So here we are with our first chapter. Our first chapter is chapter 12. On this chapter, we're going to discuss liquids, solids, and intermolecular forces. Hopefully on 1411, you were able to make it to chapters 8, 9, and 10 and 11, and you know how to identify a polar molecule, a polar covalent bond, and all that kind of stuff. And you know about Bespar, trigonal planar, tetrahedral, trigonal bipyramidal, and all that kind of stuff. Because knowing intermolecular forces is going to depend on that. So what are the objectives we are going to be doing in this chapter? First one, articulate the importance of intermolecular interactions. For that, we're going to identify the intermolecular attractive interactions between a group of molecules. We're going to compare the relative strength between different intermolecular forces, and we're going to explain how this disturbing the electron cloud can polarize a molecule and produce intermolecular forces. We call that dispersion forces. And then we're going to predict trends in physical properties due to intermolecular interactions. So once we understand the intermolecular forces, we can start predicting properties at the macro level, like boiling point, vapor pressure, and so on. And then we're going to move to the last part of this chapter, which is going to be interpret phase diagrams, where we're going to find the various changes of state of a pure substance, basically gas to liquid, liquid to gas, solid to gas, gas to solid, and all that. We're going to learn how to determine if those changes, for example, solid to liquid, is an endothermic or an exothermic process in terms of absorbing or releasing energy. And then once we understand that, we're going to be able to draw heating curve, and we're going to be able to calculate the heat or the enthalpy involved on all these changes. From there, we're going to go to phase diagrams, which allow us to understand the relationship between pressure and temperature in terms of the states, solid, liquid, gas. And to do that, we're going to understand what the critical pressure, critical temperature, vapor pressure, normal boiling point, normal melting point, and so on is. If you notice, I know you know how to read. The reason I'm reading this for you is because as part of the learning process, incepting those concepts on your mind before we actually begin to discussing them is the way to go. I'm assuming you already read the book and probably have done some of the Alex problems. So I'm assuming that. So this lecture is not to cover every single detail. This lecture is to go deeper into some of the concepts. So remember, you're teaching yourself and only helping you understand it better. So I'm assuming always that you have already read the book. If you haven't, that's on you, that's not on me, so keep that in mind. So let's talk briefly about the states of matter, and in terms of how we visualize this from the particles point of view, or the particulate theory. The main thing I want you to visualize is that on gases, the particles are going to be very separate from each other. On liquids, they're closer together now, but they are kind of random. So their arrangement is random. While when we make it to the crystalline structure or the solid, they're very close now, basically barely any gaps in between, and they seem to follow a pattern. So that's the first thing we have to visualize. In addition, these particles, as long as the temperature is not 0 Kelvin, not okay, but 0 Kelvin, at 0 Kelvin, we believe that any movement will stop. So as long as the temperature is above 0 Kelvin, these particles are always moving, even on the crystalline solid, where they are not changing locations, but they are vibrating. So visualize that whenever we talk about everything else we are going to be covering in this chapter. So the way I do this is, instead of doing all these concepts at a time, we're going to grab one of the learning objectives, we're going to discuss it, we're going to do problems on it, we're going to close it, bringing back the learning objective. And if this was an in-person class, I will not move forward unless everybody tells me that you got the concept. However, this is a blended course. So it's on you to go find help if you don't understand something after the time that is presented to you. But once more, and I'm just insisting, once more, you read the book, you did Alex, and now you're doing the lectures. So by this time, those three things should come together, and you should be understanding this very well at this point, as long as you are doing your part. So if you still don't get it, then office hours, Science Learning Center, 24/7 tutor, questions and answers on the Canvas page, and come see me at the office, whatever you need to do. But we're not going to leave you behind, but you have to come get the help. So, learning, and I'm talking so much because it's the first presentation. Once we move into the second presentation, you already have listened to my speech. So you're not going to hear the same thing twice. So back to the learning objective. So we're only going to concentrate on articulate the importance of intermolecular interactions, which means we have to understand what intermolecular interactions are. Identify the intermolecular attractive interactions. I can tell you right now that there's going to be 4 of them. And going from the strongest to the weakest, they're going to be ion dipole. Second one is going to be hydrogen bonding. Third one is going to be dipole. And the last one is going to be dispersion forces. These two combined, we call these the van der Waals forces, because they're based on the movement of electron, the polarizability of the electron cloud. These two also, I know I told you that we're going from the strongest to the weakest. These two also can change places. So we're going to see some properties of the molecules that would allow the dispersion force to be stronger than the dipole sometimes, and vice versa. And then we're going to continue talking about the polarizability and how that relates to the dispersion forces. So the way I do my lecture, you're not going to see a lot of information here. You already saw that on the textbook and on Alex. What we're going to do problems, and the concepts that are very important, I'm going to discuss those concepts as we do the problems. So let's do this problem. This is our first problem. Determine the kinds of intermolecular forces present in each element or compound. Well, what are the forces? Dispersion, dipole, hydrogen bonding, and this one is ion dipole. Whenever we start talking about mixtures, but we can concentrate now on just the ion or the ionic force. So how do we know which is which? Well, dispersion is nothing more. Imagine you have a sample, and the sample is made out of elements from the periodic tables, right? And all elements from the periodic tables contain electrons. And these electrons are always moving. They're always moving everywhere. And if it's a molecule or a compound, they are connected because of the electrons they have on the valence shell. So remember how important you were told that 1411 was? There's no way you can understand this unless you understood that. So if you need a good review on 1411, come see me. We can review everything in my office. But during the lecture, I'm assuming you already know this. So all matter contains electrons because all matter is made out of the elements on the periodic table. So those electrons are always moving. So what are dispersion forces? Well, dispersion force is one type of intermolecular interaction. So this is one molecule. So that's not what we're talking about. We're talking about interaction between molecules. And this will be another one molecule. So whatever interaction they can have, that's what we call the intermolecular force, IMF. So let's talk about dispersion first. So the electrons are always moving. So what happens is just based on probability, I have a molecule and all the electrons on a nanosecond happen to be to one side only. Well, at that particular time, this side becomes more negative than this side. By default, this one becomes more positive. However, these electrons can suddenly split in half and then it will be even. Or they can come all the way over here and then this will be negatives and this will be positives. So this negative and positive charge is always changing. So we cannot say that it's negative or positive because it's always changing. The best thing we can do is say that is partially negative and partially positive. It's not totally negative, that will have to be permanent. If not totally positive, but partially negative, partially positive. Or partially negative, partially positive, depending on where the electrons are at that time. So let's say that at this particular time, the molecule is showing this configuration, partially negative, partially positive. And the other molecule is showing this configuration. And now I want you to remember this. The relationship between positive and negative is very basic. And if you're going to go all the way into organic chemistry, knowing this concept that I'm going to tell you right now can save you memorizing thousands of pages because you're going to understand it then. And here is the concept. Positive love negative. Positive love negative. So that's the relationship we're looking for. So this side of the molecule is partially negative. This side of the molecule is partially positive. And if you ever play with magnets before, you know that when you put opposite poles close together, they will start attracting each other. So here is my intermolecular force. Because one molecule developed a partially negative pole and the other molecule developed a partially positive pole and they were properly oriented, they attracted each other. So that's what we call intermolecular interaction between two molecules or more. So that's dispersion. Dispersion is going to be based on the movement of electrons on the cloud, that as they move, they're going to create partially positive, partially negative areas in the molecule, but they're going to be fleeting. They're going to disappear right away. So that's our first intermolecular interaction. dispersion force, which is between two molecules due to the creation of partially positive, partially negative poles. What about dipole-dipole? To be able, for us to be able to observe a dipole-dipole, we're going to have molecules. These cannot be atoms by themselves. This is going to have to be a molecules, and the molecule will have to be polar. So we need polar molecules to be able to have dipole interactions. So once more, you're going to need one molecule that is a dipole in close proximity to another molecule that is also a dipole. And what does a dipole mean? A dipole means that this molecule is partially negative on one side and partially positive on the other side because of the movement of electrons, but different to the dispersion force, this partially negative, partially positive do not change. These electrons are to one side and they're going to stay there. Where do we observe that? Let's say, for example, HCl. If you remember from Chem 1, the electronegativity from hydrogen is 2.1. The electronegativity for chlorine is 3.0. If you do 3.0 minus 2.1, you get 0.9. And anything between 0 and 0.4 is a non-polar covalent bond. Anything between 0.5 and 1.8 is a polar covalent bond. And anything bigger than 1.8 is going to give you an ionic bond. So by knowing the electronegativities of the elements on a molecule, on a bond, you can determine the polarity of that bond. So since this is 0.9, that would be a polar covalent bond, which means there's a force strong enough to pull the electrons toward the side of the chlorine, the one with the bigger electronegative value, and they will stay there. The nucleus on the chlorine have an effective charge strong enough to pull the electrons that are being shared. Remember, a bond means two electrons, right? That are being shared, to pull those electrons toward the chlorine. So they're going to be closer to the chlorine, therefore making these sides more negative, not negative because they're sharing the electrons, and this one more positive. And because of the electronegativity, that configuration is permanent. It doesn't change, which made this a dipole. Why a dipole? Because we have a negative pole and a positive pole, which means two poles, which is the same as a di for two poles. So to have a dipole-dipole interactions, you're going to need two polar molecules present at that point. So let me clear the screen a little bit. So if I have a molecule of hydrogen chloride, which is partially positive, partially negative, is a polar molecule, a dipole, and I have another molecule of hydrogen chloride close by, which is partially positive, partially negative, there's going to be an interaction between the two of them. And why is that interaction happening? Because I have a partially negative in close proximity to a partially positive. And the secret of life is between negative and positive, negative, love, positive. And that's why we have our intermolecular force between those two molecules. And this is a dipole because it have two poles, and this is a dipole because it have two poles, and therefore this is a dipole interaction. What about hydrogen bonding? Hydrogen bonding is a special type of dipole. On hydrogen bonding, you're gonna have to have present fluorine, oxygen, and nitrogen. The only time where you're gonna have hydrogen bonding, those three elements have to be present. But you're also gonna need hydrogen. So to have hydrogen bonding, you're gonna have that you're gonna have that on the molecule, or you're gonna have that on the molecule, or you're gonna have that on the molecule. So you're having a lot of fun. And why is that? Well, because fluorine is the most electronegative element in the whole periodic table, followed by oxygen, and followed by nitrogen. And other elements like chlorine are going to have 3.0 also, but nitrogen is the smallest one, which means the nucleus is a lot closer to attract electrons. So you have to think about everything you learn about that. Size, electronegativity, and so on. So nitrogen have the same electronegativity as chlorine. However, nitrogen is smaller, so the attraction is going to be stronger. So these three features, FO, FH, OH, or NH, the electronegativity difference is going to be so big that they're going to create a dipole that is very strong. So if I showed you HCl like this, imagine OH to be like this. So it's very, very strong. A very dipole, it's a super dipole, let's put it that way. So the only time you're gonna have hydrogen bonding present is when you have two molecules in close proximity, oriented the proper way, where you have a super dipole in proximity to another dipole. So let's see. So let's say, and this force, the hydrogen bonding, is super important because this is the force that keeps together our DNA. Our DNA, which is a helix, the reason why it's a helix is because every so many units, there's a hydrogen bond putting it together. The same with the proteins, which is the amino acids, bringing together hydrogen bonding every so many amino acid sections. So it's a very important intermolecular force to understand. So let's say once more that we have, let's say for example, water. We know that water is a polar molecule because it's bent. We know that this is 2.1 and 3.5. The difference between the two of them is 1.4, which means it's a polar covalent bond. So we can do something like this on this side. We can do something like that on that side. And when you have two forces acting together on that configuration, they combine to give you that. So a better way to represent water is like this. Those two forces combine to give you something like this. So this part is going to be partially negative. The part where the hydrogens are is partially positive. So that's basically you applying what you learned on 1411 on how to determine that a molecule is polar. Because to have a dipole-dipole or hydrogen bonding, which is a special type of dipole, the molecule has to be polar. Do the Lewis structure, using the Vesper theory, determine the shape, determine the polarity of each bond, see how those forces interact together, and then you can say that water is a dipole. So now we can draw water like this. If I have a molecule of water, we know that this is going to be partially negative, partially positive, and I have another molecule of water, partially negative, partially positive. We just brought into close proximity a partially positive, negative to a partially positive, which means there's going to be a force attracting those two, which creates our intermolecular force. And the intermolecular force is between a dipole and a dipole. So this is a dipole-dipole force. However, it's a OH. It's a super dipole. So we're not going to call it dipole-dipole. We're going to call it hydrogen bonding because it involves the interactions of two super dipoles. Remember, you always have to have fun to understand this, right? You gotta be able to find fluorine hydrogen, oxygen hydrogen, or nitrogen hydrogen to even be thinking about hydrogen bonding. And that's what we found. We found one of them there. So understanding that waters can do hydrogen bonding is going to explain very soon why water is one of the molecules with the highest heat capacity, why the boiling point is so high, and so on, because hydrogen bonding is one of the strongest forces between the four of them. So the stronger that force is, the more energy you are going to need to separate the molecules. So if you have a liquid where the molecules are very close together, if you want to make it into a gas, you're going to have to separate the molecules. So you're going to have to disrupt the intermolecular forces. And what about the last one? The last one is the ionic force. So the ionic force, let's say that we have let's say KCl. This is a metal. This is a non-metal. So you know from Chem 1 that this is an ionic compound. So when you have ionic compounds involved in what you are trying to evaluate, most likely you're gonna have this is positive, this is negative. Most likely you're gonna have an ionic intermolecular force, because once more you brought into close proximity a negative with a positive, therefore creating the intermolecular force. So intermolecular force is not a bond, it's just an attraction. Even on the hydrogen bonding, it's not really a bonding, it's an attraction between the positive and the negative area. However, to have hydrogen bonding, you really do not need to have an ionic compound. Because what happens if we have HF being attracted to another HF? Well, you're going to say, well, that's hydrogen bonding. And you're right. But also, let's consider this. 2.1, 4.0, 4.0 minus 2.1 is 1.9. and 1.9 is bigger than 1.8, which will make this interaction have an ionic character. So now that we get that, let's look at this. First, krypton. And we're looking for intermolecular forces. So it's not just krypton, it has to be krypton with another krypton. So what type of intermolecular force do we have between krypton and krypton? Well, let's see. Dispersion force. All matter contains electrons, so everything has dispersion force. So we're definitely going to have dispersion because krypton have a bunch of electrons going around all the time. So if there happens to be more to one side, then this is partially negative, partially positive. And you can have an interaction with another krypton where they happen to be partially negative, partially positive, and you get your interaction right there. And since the electrons are moving, that can suddenly disappear and the interaction is gone. So that would be dispersion. What about dipole-dipole? Well, to be a dipole, you have to be a molecule. Krypton is not a molecule. Krypton is an atom, so it cannot be a molecule. There's no bond within one krypton atom. So it cannot be a dipole-dipole. And to be hydrogen bonding, you have to be a dipole-dipole. It's a special type of dipole. So the only thing going for krypton is dispersion. Krypton can only exhibit dispersion with other krypton atoms. What about nitrogen trichloride? Well, for us to do that first, we're going to have to see, well, with nitrogen trichloride, with another nitrogen trichloride, we're trying to see what is the intermolecular force present between the two of them. Well, we know it has dispersion because anything with electrons have dispersion, so there's no question about it. Dipole-dipole. To be a dipole, you have to be a polar molecule. Is nitrogen trichloride a polar molecule? Well, let's see. Nitrogen is going to be 5 valence electrons. Chlorine is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. So we're going to see the same on both of them. So all 3. So the Lewis structure is going to be N, Cl, Cl, and Cl. However, to know if a molecule is polar, you cannot stop there. Now you're going to look at the Vesper table, valence share electron pair repulsion table, and you're going to see that the central atom have bonded. It has 3 bonded atoms. 1, 2, and 3. So bonded, it has 3. And it has 1 lone pair. We're only looking at the central atom. Lone pairs, 1. So now that we know that this molecule have a central atom with 3 bonded atoms and 1 lone pairs, the table is going to tell us that it's going to be trigonal pyramidal, the molecular geometry, which means the proper way to draw it is going to be like this. And now that we have the proper shape from the Vesper table, now we can say, so this is 3.0 and this is 3.0. So the difference between them is 0. So this is a non-polar bond. So that means I cannot do arrows. There's no arrows because the bond is non-polar. So there's no vectors for us to compare. However, when we look at the molecule, we can see that this molecule is not symmetric. We can see that these electrons here, which is nothing more than a big orbital, is more negative to one side than the other. So not because of electronegativity, but because there's a pair of electrons on one side all by itself, this is going to have to be partially negative, partially positive. So this is a dipole. So this molecule is going to have dispersion. It's a dipole, so two of them together is going to be a dipole-dipole. In addition to that, it doesn't have any hydrogens, right? So there's not going to be any hydrogen bonding. Even we had the nitrogen, but there's no hydrogen there. So there's no hydrogen bonding, and you can stop there. So the only thing going for nitrogen trichloride is dispersion and dipole-dipole. What about silicon tetrahydride? Silicon tetrahydride is a molecule. So anything we have, so we're talking about the interaction between one silicon tetrahydride with another silicon tetrahydride. So what intermolecular force are we going to have attracting them together? It contains elements, so no doubt about it. It's going to have dispersion. Dipole-dipole. Well, the molecule has to be polar to be a dipole-dipole. So is this molecule polar? Well, let's do the Lewis structure. Silicon, group 4 electrons. Hydrogen, group 1. So the Lewis structure is like this. But do not stop there. You have to draw it the proper way. So using the Vesper table, we see that the silicon, which is the central atom, have 4 bonded atoms, and lone pairs, there's no lone pairs there, so 0. So when you have 4 bonded atoms and 0 lone pairs, the Vesper table tells you that this is going to be a molecule with a tetrahedral molecular geometry. So now that we know the shape and the Lewis structure, now we can draw it the proper way. So that means it's going to have a hydrogen going that way, a hydrogen going that way, one coming toward you, and one going behind you. That's a tetrahedron. So the other tetrahedron is going to have the same thing. So is this a dipole interaction? Well, let's find out. 2.1, 2.1, 2.1, 2.1, and if I remember right, silicon is 2.4. And you can double check that later on your electronegativity table. So the difference between these two is 0.3. So there's no polar covalent bonds on this molecule, so this molecule cannot be polar because there's no lone pairs either. Well, let's say that I get these numbers wrong, and let's assume that this is 2.6. So if this was 2.6, then this will be 0.5, which means it's a polar covalent bond, assuming that those numbers are right. We don't know, because I don't have the table with me. But that's not the point I'm trying to check. We have a force going that way, a force going that way, and a force going that way. So imagine that you're sitting on a chair and 4 people are pushing at you from those 4 directions with the same amount of force. Would the chair move? And the answer is no. All those forces are going to cancel each other. So the distribution on this molecule is even also. So even if those bonds were polar, because it's a tetrahedral with no lone pairs or anything like that, because of that, this molecule is going to be non-polar. So therefore, this is not a dipole. So the only thing that you have going for it is dispersion. Because if it's not a dipole, it's not going to be a hydrogen bonding. Hydrogen bonding is a special type of dipole, a super dipole. So far we have this dispersion for this one, dispersion and dipole for this one, dispersion for this one, and we already see this one. We know that's going to be hydrogen bonding because you have HF with 4.0 and 2.1. The bond is a super polar bond, which is going to make this like that. And if you have another one like this, you have two super dipoles. So the attraction here is going to be the intermolecular force here is going to be hydrogen bonding. So what are you supposed to do at this time? At this time, you're supposed to think to yourself, yeah, I got it, let me press on, or no, I didn't get it. So this is recorded, so go back and forward until you get it, or me repeating the same thing over and over is not going to make it clear, right? Or come see me at the office so we can clarify for you. Go to the Science Learning Center, go back to the textbook and review it. Go back to your notes for 1411 and remember how to do polar molecules. Whatever you need to do, you have to take charge. You have to decide, yes, I need help. Only the courageous people dare to look for help because they recognize the weakness and they know how to improve. So I challenge you to be a courageous person and go look for help at all the resources that we have. So once you feel comfortable that you know it, then do the daily work. So this is your first daily work. So at this point, what you do, you pull out a piece of paper, you write down 12.1, and you do this problem. And as we go into the other lecture, you continue with 12.2 and so on. When we're done with chapter 2, totally done with chapter 2, which is going to be several recorded lectures, then you scan that or save it as a PDF file and you upload it into Canvas. And remember, this is 5% of your course grade. So we're going to stop here. I was trying to do these videos in around 15 to 30 minutes. This is close to an hour. So this takes time to understand it, especially when we had to review 1411 first. So let me stop here right now. Review this video. I will be posting the second part very soon. So see you later. Take care.